We'll just wait for a few minutes and then start. In the meantime, if you guys have any questions, feel free to ask me. Okay. I'll just recap whatever we covered last class. Okay, we looked at lambda functions. So before that, a little motivation. So first of all, I declare a variable m, okay, that will, yeah, excuse me. Yeah, so I declare a variable m that I set to be 10, okay. So this will be my divisor, okay. And then another variable, I'll call it as remainder, sorry, I meant a function, which takes input as integer n, okay. And that n, when divided by m, okay, you get the remainder. So that's what something gets returned. Okay, that's the remainder function. All right. Um, so it's a pretty simple function, right? And so this is the example, and we'll keep building on top of this. Okay. So the idea is that the thing that you are dividing, the number you're dividing, okay, that number is variable, and the number you're dividing with is a constant. Okay, so that's how we will take the example forward. Okay, so if I print so in my main function, if I print the remainder, okay, calling that function, then it shows, like, if I pass 15, it will just give me 5. Right. Okay, next.
Yes.
Yeah. Uh, then I'll take the same example and then convert the same plain function, which is the remainder function, to a struct now. So the idea is that we apply the same principles here, but in a different way. So inside a struct, whenever we declare a member variable, it is private. Okay, and that does not change. So we'll use that fact when we construct the object for that struct, sort of like a class. Okay, so the rem here is the object, and I declare that and I define this struct. So I use the struct keyword, then the name of the struct, which is the remainder, and the name of the object, which is rem, and I pass a number. So that number is, so here, hence the constructor gets called, okay, where the underscore n is set to 10. So that is the input it takes, okay. And then after that, so this is the syntax for setting so when you have, when the constructor gets called, you can set variables, internal variables like this. So I use m and set it to underscore m. Okay. So the value of 10 is now set, that is now the m is now set to 10. It's pretty much similar to the example we saw here, where we do not change m. And for this object, the divisor small m gets permanent. It's like set. Okay. We'll use a
Yes.
very, yeah. So we'll use a very similar looking way of calling this function. So the function, usually the signature of it is the name of the function, then you use small brackets and then pass a number to it. Okay, so that'll be like 15 or whatever. Like in this example, it's 15. Now I write a specific function with the operator keyword and use this small brackets to define the objects function. Okay, so for now here, it's the object, but when I write it in this way, here I'm calling its constructor when I'm creating that object. When I use rem again and I use this braces, I'm actually calling this function. It takes n and returns n percentage m. So if I pass 15 again here, and because I had set small m to be 10, so dividing, I get 5. So this also returns 5. Okay. So remember, the difference here is that here the constructor gets called. Here the operator that we have defined in this way gets called. So pretty similar to the remainder function that I've written. I could have actually written a remainder, but maybe the remainder name would have been confusing. But anyway, the point is Here the object itself acts like a function. Okay, so this is a plain old um, function that we know of that we can use to in some statements like print statements like here. Okay, here I'm using the object itself to as a function. Okay, so that's the other way of doing the same thing. So this will again motivate towards a class. Okay, so
Yes.
right, yeah. So here I used a struct as a function. Okay, now we'll use a class to do the same thing. When you use a class's object as a function, it's called a functor. So that's what this class, and I just call the class itself also a functor. Okay, but essentially this is what a functor looks like. The outputs. So here the functor's object is func. So the func itself acts like a function. Okay, when the objects you use this sort of small brackets. Again, the definition also relies on the fact that the operator, the small two brackets are defined. That I have defined in this way. It takes input n and gives some output like n plus 5. I could have given n percentage m also, but anyway, the point here is you can do pretty much the same thing that we did here before with the remainder function using a functor. Okay, next. The difference here is that the small brackets are the input parameters. Okay, so the syntax for it looks something like a function. Okay, if you have the big brackets, which you might have seen being used for, let's say, standard vector or standard arrays and so on and so forth, there it more or less like it mostly it means a dereference operator where you're accessing the ith element of the array. Okay, the
Yes.
offsets, yeah. So the offsets there are determined by the data type of the vector or the array.
Hmm.
But the idea is that the ith element gets accessed, and then the convention is to use the big brackets. Nonetheless,
Okay.
you can actually define that same bracket, okay, to
Hmm.
your function and use it accordingly. So here my output will be 9. It's not a function, like it's not some vector that I'm dereferencing here, but it's actually up to me how to define this sort of an operation. Okay, so
Yes.
this is the distinction I would like to make here. Um, that yes, the syntax for functions does look like this, and dereference operators look something like this. But then again, it's completely up to you how you want to define each of them for your class. Okay,
Yes.
yeah. So the idea is that just because something looks like what we're used to it does not mean it is actually doing the same thing. This is what I'm getting at. Now,
Hmm.
the other thing is I can have a plain old simple function. I'll just call it increment. And this is always there. So the function func it's not actually a function. It's an object of a class called a functor. So it also behaves like a class. So it has its member functions that I can
Hmm.
call by passing like 5 and so on and so forth. Okay. So that's also there. Okay. Moving on. Now we come to lambda functions. So lambda expressions have certain parts of the syntax. So for any lambda function, the syntax looks like something like this, where there is a capture list. Okay, so the capture list with the big brackets. You use that's the capture list. Then we have the parameter list that will be the small brackets, and then yeah. So then the return type. Okay, with the body. Okay, so this is sort of the syntax for it. We'll see how each of them actually works. So plain old. Let's go to this example itself. So let's say I define some function, okay, called print, and we saw auto keyword before, okay. So we'll be using that keyword as a placeholder for whatever data type my body should return. Okay, I really don't need to worry about whatever complicated data type it should have. I can just put auto and just forget about it. Okay, there is no capture list and no parameter it takes. Okay, just that there is a body. Okay, inside that body, I just have a plain old standard cout with hello world. It just prints hello world and no fancy thing yet. Just that it just prints hello world. Whatever will be the data type return of it or to takes care of it. So I don't need to worry. Now, this whole thing from here to here, okay, has been defined to be a lambda expression or a lambda function. Okay. So to use this function multiple times, I've saved this whole thing into a variable called print. Okay. So to use this variable, or I can think of it like it's actually a function also. So to use this function multiple times, it's basically it's again the same syntax. You call the function with the small two brackets. Okay. Again, the syntax for a function does not change. It's still the same. And the number of times you call it, it prints hello world that many times. Okay. Moving on. If what I'm claiming is I'm claiming that this portion from here to here is the print function, that lambda expression that I have stored. Okay. Because of that, what I can then do is have the same expression and then use the small brackets, okay, to in a way actually call that function itself. Okay. As in, I'll have from here to here the same exact lambda expression, okay, what I have defined. And because I've saved it into print, instead, what I can then do is just call this with the brackets. Yes, it might not mean much because it's just a standard cout. I don't need to have all these extra boilerplate looking things. True, but just so you understand, you might have some code which does something in a very just maybe once, and this can be done. Okay, essentially that's what I'm getting at. This also can be done. You can just call it once here, and this will print hello world. Okay,
Yes.
and then I took some other examples where inside the if statement itself, I had lambda expressions where first the capture list. So again, I'm giving it empty. Will not worry about it. But this time we'll worry about the parameters 1 and 2 that my lambda expression will take now. Then with the brackets, again, pretty similar to the previous one. This time I'll have a return type instead of just print statements, where the return compares A and B. Okay. And again, to use this lambda expression from here to here that I've highlighted, I use the brackets, and then I can't just keep it empty because the lambda expression expects two inputs. So I have to pass two inputs. Okay. Then the if else statement gets executed, that is straightforward. Next, I am checking inside the cout itself. I can have a lambda expression, okay, something like this, where there are two inputs. The capital list is empty again. The return type, okay, is this expression, which if we further break down is it compares A less than B. If it is true, it returns A, or else it returns B. Essentially, it is returning the lesser of the two values that you're passing. And we are using the parameters, okay, the function parameter syntax, and passing 8 and 6, and it'll return the lesser of them. Okay. Furthermore, what I'll do is put the same thing now, okay, this expression in a clause sort of a function, lambda expression, and then call the same statement that we had seen here using this clause function. It makes it a little neater than writing the same lambda expression in multiple times or whatever. So yeah, that's some of the use of lambda expression. They're reusable. They're like it's a very similar one. Again, can argue that if we have functions, then why do we need lambda expressions? True. Thing is, sometimes you want to keep your the function list clean, and sometimes you just want to throw a function. Okay, and many times you might just want it limited to a certain uh, piece of your code only. Okay, because if you want to write functions, you have to put it outside the main and so on and so forth. It makes it a little messy. You can even segregate your internal functions, something like this, okay, and then use it multiple times, and then after it's done, any of this will get destroyed. Okay, all right.
Yes.
So that's the syntax for clause and everything. And then moving on, so we'll come back to the same example that we saw at the first, the remainder operation, where we'll use lambda expressions now to do the same operation. I'll have integer m equals to 10. Okay, that does not change. Okay, now I'll use auto again. Because I don't want to worry about the return data type of my uh, lambda expression. So the remainder function will be there. This time, if you see, I have my capture list capturing m. Okay. Again, it takes integer n as the input parameter, and the return is this. Pretty straightforward. But the thing to remember here is once the capture list is how does the capture list work? So capture list captures the value of whatever variable you pass. It takes the value of the variable at that instance. As in, because I'm passing here m, okay, and m has been set to 10, it will capture m as 10. And anytime I call remainder, okay, so for example, here I pass 15, which will be the value for n, which is variable, which can change, okay. But for this function, this body m has been set. Pretty much behaves the same as we saw before here. Sorry about that. Okay, anyway, yeah, that's fine. Yeah, so if you see this example, I had m as constant, and the other part was that the divide the one way, I think it's not divide. Anyway, so the one way dividing, okay, that number is changing. Pretty much the same thing. We're doing it here. So we're passing 15. And because of the property of lambda expression that the capture list captures the value of the variable at that instance, it sets it to 10. That's it. Plain straightforward. Next, I set, let's say, to actually test this, I set m equals to 5. And if you call this function, it won't use m, the value of m as 5. It will use 10. Okay, because this is where the remainder function was set, as in this lambda expression was created. Okay. And but if I take this example of lambda expression, which pretty much is basically this one, where the lambda expression has been written and I'm passing 15 to it, this will give me answer 0. Why? Because m is set to 5, 5 gets captured here for this lambda expression. And it expects the input as integer n, which I'm passing as 15. Similar, the same input as here, but and I'm printing something, right? And that same print is also happening here. But the difference is here this lambda expression captures the value of m as 5. So the answer differs here. Okay. Then yeah, there's another way you can pass capture like a variable as a cap for the capture list using a reference. So the difference here and here is that the value that of m that we passed here was passed by value. Okay. So when you pass by value, the value only gets captured. Okay. But when you pass it as a reference, it takes the value of the variable at that instance. Okay. So as in, because it's a reference inside your body of your lambda expression, okay, this variable is treated as the same variable that we had defined before for it to pass. Okay, because it's a reference. So with this, you can actually write a sum, okay, where you're passing some n value for n, and it keeps adding to that temporary variable. All right. So if I have sum as 15, it adds 15 to the original value, which is set to 0. So this will print 15 and then plus 15, 30. This will print 45. This will print 16. The reason that so one should note here, even if I had called this remainder function many times, the value of m would not have changed, but it does change here because of the reference passing by the to the capture list. Okay. Now, yeah, I think, yeah, that's it. Yeah, that's all I wanted to say. Moving on to the last example. Okay, last one, but one. I'm setting the value as 0. Okay, so the important thing to note here is what? So, okay, I'll take this example as something called check. I've set two integers, val and ref. Ref I'm passing as a reference. Okay, val is passing my value, so I'm calling it val. Initially, it is set to 0. Okay, for the body expression, okay, val is a constant. You cannot change the value of val. Okay, reference you can change. You have to pass it by reference. And anyway, in parameters that you have passed, you can change. I mean, anyway, they will be passed. You can change them, but it doesn't make any sense. As in, they're just limited to this scope, so the change will not affect anything anymore. Okay, so printing val, ref, parameters, everything. I have this example where initially val and ref were set, val was set, ref was just declared. I'm setting ref and then printing check 10 and 11. So then you can try guessing what will the outputs for val, ref, parameter one, parameter. Basically, whatever it prints for this statement, sorry, for this statement, then again for this statement, and then again for this statement. Okay. This is the exercise we did last time. Can go ahead and do it. Yeah. Moving on. So last example I showcase here is pretty much the same as before, but this time I'll do the same things, but using a struct. Okay. So I'll do, drive home the message that lambda expression makes this so simple and just a few lines for doing the same thing. For doing this exact thing, you have to write a whole struct class and then write the check function, which will be the object of it, and then call everything. Okay. I'll quickly gloss over this struct. So the check underscore f is the struct name of the struct. It has two members, val f and ref f. This is a reference. So check f underscore f here is a constructor with taking val and ref as two variables, some values. So here it will be passed by value, here it will be passed by reference. Then it sets the internal member variables. Then I set the operator with these brackets. So it sets this function, okay, using two parameters and then prints this. Pretty much the exact same thing as here, but now we have to use the properties of struct to achieve the same thing. It requires a lot more boilerplate code. Okay. The last thing is you have to declare the object also. So this is the uh, name of the struct. So you can just use name of the struct, pass the values that we had set before, and check will be the object of instance of that object. Okay, instance of that struct. Okay, this is my object here, and then call the same things. Okay. So yeah, that's what we covered last time. Okay. Any questions so far? Okay. If no
Yes,
questions,
yes. No,
yeah.
no, no.
Okay, no question. Okay. If no questions, I'll move on to today's topic. Okay. Yeah. So done. Just give me a second. Yeah. So today we'll be covering smart pointers. Other than lambda functions, I think these are so lambda functions and again, obviously, object-oriented programming is a very big part of C++. But if you take the modern C++, smart pointers are like very, very important. And that's what makes memory management issue which usually plagues C, right? And to some extent, even C++, if you're using older versions, much more simpler to handle, okay? Because there is a sort of an automatic management of memory that happens, but without any garbage collection, okay? We'll see how efficiently sort of memory management happens in C++ if you use these modern features. Okay, so yeah, let's start. So I'll have the ice stream as usual, we printing stuff, so a header file is required. I'll have my class. Then I'll define a public access of a function. I'll just call it function. Okay. Doesn't have any body, it doesn't take anything. It's just a plain old function. Then I have my main. I'll declare an object obj of this my class. Okay. Next, let's say I'll give an example where I will have my class pointer. I'll declare a pointer to this object. Like I'll call obj pointer, which is of my class pointer data type. Okay. As in it can store it points to a okay, it stores an address, right? But that address will contain the my class data type of object. Okay, think of it like integer variable, so integer a or integer b or so on and so forth. But we also declare integer pointers, let's say ptr. Now ptr stores the address of a, okay, so as to point to a. Pretty much the same thing, but instead of integer, here we are using custom data types. Okay, so what I will do is do this, use the new keyword, okay? Because in C++, okay, you can, I think, use C style. So I'm just using the C++ way of declaring new as in, okay, so what new does is, sorry, this should be not object, my class. Okay. So what this tells is, I have a class called my class, okay? I'll use the new keyword to create an object. I have not given a name to it yet, okay? But what this whole thing will do is it will pass a pointer to that object. Okay, that's what I'm trying to store in object pointer, right? Okay, so this creates ownership of, so the owner is object pointer now, pointing to some object, okay, of data type my class, right? So it's here I'm saying that my object pointer will be of data type my class pointer, okay, not a problem. Then I'm saying my class object, I'm using new to it, and that returns the pointer to that object, okay, and then just stores it in object pointer. All right. Next, I'll have sorry, that what I'll do is I'll set this object pointer to null. So a really bad thing just happened. What happened is this object pointer was pointing to an object which had its memory allocated and everything, as in that object. The thing is, it's a very plain function, but you can imagine it might have had member functions, member variables, then member functions, public parts, as in portions of it which are public, portions of which are private, protected, and so it could be derived class of some base class, right? Whatever maybe the case. But what happened here is if I just had object pointer, I can actually change the pointer pointer's address to anything actually. I could reset it to maybe something else. I just set it to null. Now what happened is you had a memory leak because now that object which is created was not properly destroyed, and that just dangles some in memory location someplace, and nothing is currently pointing to it. Okay, so this is a valid code, and it causes it to lose ownership. Okay, So this was memory leak in assignment example. Oh, I hope this is clear. Then moving on to another example, I'll give error with copy. So there are different ways you can run into issues with pointers. So I'm just giving one of like each one. So let's say I have this my class pointer. Okay. This time I'll call it A, let's say, and store some object using new keyword of my class. Okay. I'll just store it in A. Again, this creates ownership. Okay. Then I can have, let's say, my class pointer B equals to A. All right. So what this did is, so I can do it this way. Use object pointer to store it. So in this case, okay, yeah. So I declared object, I declared a pointer A, and object pointer was already containing some object of my class. Now if I set to this example, okay, let's forget about that. So if I take this example, this object pointer now is set to A. This is perfectly valid because A is updated at my class pointer. So this is first object, this is second object. Now second object gets returned to first object. And now again, the first object has no ownership, as in nobody's owning it, and it's just dying. It's just there in the memory. Okay, so there's also another example. Loses ownership. Okay. Not just with null pointers, you could reassign it to some other object of the same build type and it will lose ownership. Okay, so you can run into issues like this also. Another example is, let's say you declare my class pointer B to the declaration and set it to A, let's say. So this is copy ownership. I'm copying the ownership as an A was pointing to some object, right? Some second object. So this is first object. Now A is pointing to some second object. That address now is also in B. Okay, so B is owning that, right? This is of copy ownership. Now I could set A to null. Okay, so A won't point to that object anymore, but B will. Okay, so this example, it could, I mean, one can do this also, but what if I just delete B? Okay, so what this will do is, now, okay, I'll repeat myself. This is the second object. Now that we are storing it in A. Okay, so A is pointing to that object, this object that I'm referring to. B also, now if you declare B and equate it to A, it will copy that address, okay? And B also is pointing to the same object, right? So essentially there is a, so you can forget about this object for now. Think of this object, which is the only object in focus for now. Two pointers are pointing to it. First of all, A was pointing to it. Now B is also pointing to it. What if I delete B? What it will do is it will take care of deallocating all the memory for that object, okay, of my class, right? It will deallocate all the memory, all the functions, and whatever deletion has to happen, it will take care of everything. Okay, but let's say you do the same thing with A again after doing with B. Then you're running into an issue because already B, which was pointing to this object, has been deleted. Now you are deleting A, which is actually not pointing to anything. Okay, so this is called double deletion, and this is also error in C++. So this one deletes the object pointed by B and removes ownership. Okay. There is a solution to it. So which is valid as in it is available in C++. Okay. You can do it. There is a check for it. You can do a check and then do this deletion. Okay. So to avoid this error, so I'll present that solution first, so that when we discuss smart pointers, which actually take care of all these sort of issues automatically, you'll appreciate that solution much more. Okay. Anyway, in any case, this is also a solution which one can do. So let's say the function was there. So I'll define it fun. Let's say my class pointer A is there. Okay. And let's say it is set to 0. My class pointer B is there, set to 0. What I will do is outside, I'll call it try clause. I'll use the try function, try and catch function. A equals new my class. Okay. And I'll call the function of A. So essentially, let's say I want to call the function of A. So this function, I just want to use it. Okay. Then what I can do is set B to be my class. I'll also do the same for B. And then catch if this does not happen. I mean, this is an example. You can, I'll have some check here. Let's say delete A and delete B and then throw. If it runs into issues, you can just throw and yeah. Or outside then, if it does not, if it tries to run, if it does not, if it cannot, and tries to catch if it deletes, else you just delete it. Yeah. Okay. So just yeah. Right. This is a try and catch way of doing the same thing. Okay. So now let's look at um, how we can do sort of a similar thing, but we're using classes. Yeah. I'll use two concepts in C++. One is RAII. Okay, I'll write the full form of it. It's resource acquisition. Sorry, it's initialization and RRID resource release is desktop. Okay. What is this and how does it help us or anything? Well, we'll come to it now. So let's say I have a templatized class. Okay. which takes class itself, some T as parameter. The class will be a smart pointer for us. Okay. I'll have a private portion of it. So it will be pointer PTR of data type T. Okay. The public portion, smart pointer itself, the constructor, okay, takes T underscore PTR, so which we want to set it to, and then sets PTR to underscore PTR. Yeah, that's uh, the body. I don't need to have anything, so I'll just keep it empty. Okay. So this is what we call as RAII, as in when resource gets acquired. So as in you acquire when the resource acquisition happens, as in you acquire the resource. Okay, that's when you initialize. So this is the portion of RAI. Okay, I repeat it again. So the smart pointer is this portion is the constructor of this class. Okay, the data type is T, some capital T. Okay, so that is determined by the template of the class. Now, the underscore PTR will be the variable that is acquired. Okay, when the acquisition happens, as in the constructor gets called. Okay, in short, you can also think in this way: when the constructor gets called, PTR, which is the internal variable, gets set. Okay, so this resource allocation of underscore PTR is when initialization of PTR occurs. Okay, so this is the first step of smart pointers. The other is um, yeah. So what I'll have is I'll use this tilde. So this is the constructor. Very similarly, you write the destructor using the tilde. Okay, and then give. I don't need to pass anything actually. I just want the destructor to get called. I'll use delete PTR because it has acquired PTR. Okay, it has access to its own member variable that I just delete. So when this object gets out of scope, destructor gets called and automatic deletion happens. Okay. So this is exactly what is our ID, or resource is released in upon destruction, or resource is released when the destructor of this class gets called. Okay. Furthermore, okay, maybe I'll have void function. Okay. Doesn't do anything, just exit. So this is my class. I'll make name. So now I'll declare the object of it, the smart pointer. Remember, it wants to take an input, right? So what I can then do is pass this. So just for I won't be linking it together, but think that this my class sorry. Yeah. So think that this my class is accessible inside this. So I'll pass this class itself as the data type as T. Okay. Pretty much same here. So instead of just my class pointer, okay, I'll have my class pointer PTR as internal member variable. Okay. This smart pointer, I'll call it as S. Okay. And the constructor expects underscore PTR, right? So I can just do my class again. New my class, it will return a pointer, okay, for PTR to copy. And then resource got acquisition happened, right? So because the constructor got called, so initialization of PTR will happen. So now this new my class, which just got passed, gets stored inside PTR of the object SP. Okay, I'll end this line now. So now Okay, so this I can just ignore. I can actually do this. So I can call function because function is a member of my class and SP is an object of this class, right? Right. So to use member function of that, so I can just call SP. Okay, so there is one more line actually I need to do. So I will do it this way. So every time I have this operator, this one, okay, I have on some lines with return pointer. As in, whenever I call this arrow function of this object, this class, will return PTR. So PTR gets returned, right? So PTR's function now I can access because PTR is my class data type. Okay. One thing I can then do is pretty much the same, but now there'll be reference here. This will also have references, and the return will be dereferenced PTR. The pointer will just get dereferenced. Okay. So this is some of the ways you can access the member variable, but nonetheless, what I'm trying to get at here is if I write a special class, okay, for this pointer, I can control when it gets created with inside SP, okay, and I can then use the pointer because it's an internal member variable. I can keep using this PTR to access my class, okay, its function and so on and so forth. Like just as I did here, I can also do it this way. So I can access SP dot PTR, okay, and then that itself I can because it's not private here, okay. I can't do it publicly, but let's say it was public. You can think of it this also. I'll access that PTR, then do the dereferencing, okay, as an access the member function of this class, right? I can also do it that way. But the point being, after all this is done, right, the scope ends for main. So when the scope ends, the member variable, for example, SP here, right, its destructor will get called. So when the destructor gets called, it deletes the pointer and this pointer is no more dangling. Okay. So the acquisition of resource and its deletion is automatically done through the constructor and the destructor. Okay. So that's the nice way of doing the same thing as we could have. Basically, this example was to show that one could run into issues in while dealing with pointers. Okay. And one solution to avoid this is have try and catch. So yes, that is possible, but we we can actually use the features of C++ to automatically handle it. So we can just write a class which acts like a smart pointer and does everything. Okay. To be honest, the actual smart pointers that we look at also do the same thing. It's pretty much something like this. Okay. So let's just use some inbuilt smart pointers that come with C++, modern C++. Okay. Yeah. Absolutely. The abstract, I call it foo. So the constructor of foo. And see out. foo printed. This is just to show what gets called actually. So if the constructor gets called, it will print foo, right? And if the destructor gets called, it will print something else. So that will be with the tilde foo. Okay. Now void bar random cout. So foo is the class, bar is the function and the function of it. So what we're doing is we are calling the bar function in the namespace of foo. Okay. Again, this is a struct, but the idea is still the same. It essentially is a class. Void f takes const foo. Okay. Circles. Then the body. Yeah. This time I'll have print this. So it will print actually this. So const foo ampersand. Okay. And then just end the line. So this is just to say that this function is now getting called. Okay. Now coming to the main function, I will use something called standard unique pointer. So this will create a unique pointer, okay, which takes foo as the class, right? So it's a smart pointer. I'll just call it as SPTR. To do that, you use something called make unique. Make unique. And call it foo. And then close the package. Yes. Okay. So this syntax of standard pointer, standard as in standard unique pointer starts from C++. What is the yeah, C++ 14? Okay, where your SPTR owns object of. Okay, pretty similar way. You can also use another syntax. It's from standard C++11. So use unique pointer to, okay, give a pointer, right? So far it is all the same, but you pass to the constructor, right, of SPTR new foo. This is what we saw before. Okay, you can use the new keyword to create an object of foo passed to the smart pointer, and then the unique pointer will take care of making it always unique. Okay, I'll explain what a unique pointer is more specifically, but the idea is that there is a single object that S pointer will point to, and when S pointer gets out of scope, that will get destroyed. So that's what standard unique pointer will do. Okay, so it's pretty much these two lines do the same thing. The difference being here it takes a pointer using new, okay, but here it makes a unique pointer and then sets it to as pointer. They do the same thing, but that's just that the syntax is different and the meanings are different. So this is from C++11. And again, here also, as pointer owns the object of foo. Okay. One can also do it this way. Have foo pointer as this S pointer. But this is what we want to sort of avoid. So originally one would do this way and set it to some new, right? So that's what we saw previously. We declared an object of data type, some class pointer, and use a new keyword to set the object to the new data type. Okay, of the to some object of that data type. You can do the same thing here, and these are called raw pointers. Okay, and smart pointers essentially want to avoid these things because they can run into issues. Okay, now one can do a check if smart pointer. Okay, as if it's, let's say this is not null. If it cannot make unique, it will return null or something. So if it is true and it passes, okay. So what I can then do is I can call the bar function that I had declared before, okay, and then just that's it. If not, oh, sorry, my bad. This is, yeah, I won't have an else statement, so I'll just do this. Okay. So the if part just ends here. As in, I checked that if s pointer is not false, so as in if I do return type, as in if let's say s pointer is empty, so it will print it will return false, and this line won't get executed. Okay. So with this smart pointer, then I can just uh, call a function, a member variable of like bar, okay, of foo. Again, here also I'm taking a liberty that I'm calling whose objects bar. I hope you understand. Pretty much similar to something like this. I'm calling the function, which is member of the template class that I'm passing. Okay, pretty much similar here also. But now the thing I'm trying to get at is the s pointer. If it is empty, this would have thrown some errors and caused issues. With the check, you don't have to worry. It will only print if the s pointer was actually allocated. Okay. Now what I'll do is use scope itself. Like I just had some empty scopes and I write some code inside it. For example, you can have standard unique. Um, yeah, standard unique pointer. It's template foo. I have another Q pointer. Yeah. But this time I'll use the standard move. Basically, it moves. Sorry. Standard move is used to move the point, whatever object S pointer is owning, now to Q pointer. Okay. So because of this, now Q pointer owns object. Okay. If you try to do S pointer bar, that is uh, not allowed because now that has moved, object has moved. But what I can do is I can call this function which expects the foo with a reference, right? So I can dereference Q pointer and then call f. That is allowed. And I can do another thing. I can move it back, right? So pointer equals to standard move. But this time I'll move Q pointer. Okay. Remember, Q pointer only existed inside this scope. Okay. So I can sprint destroying Q pointer. Okay. I can have again the check, right? After all this. Now, because of this standard move, S pointer now for that. S pointer is now pointing to that object. I'll have S pointer check and call this function again to see if I can actually do that. Okay. Another thing to note, Q pointer had the scope of from here to here. Okay. But this unique pointer, S pointer, had the scope from here to here. So at this end, S pointer goes out of scope and gets destroyed. Okay. This is when I think try and run it to see the example. So I'll just do that. I made a mistake. Oh yeah, this is part. My bad. So let's look at each of them one by one. When you create the object, right? So the constructor gets called. So foo. So this is where it gets called, right? So it tries to make object of foo. So the constructor will get called. That's when the foo gets called. Because this was successfully created, okay? And when you have the if statement, that will be true, okay? Because S pointer actually has an object. When you call bar, okay, it prints foo colon bar. So that's what gets printed, okay? When we go to this case, right, it prints f q pointer because we moved to, so we made unique pointer q pointer also of unique pointer, but this time because it is unique, okay, I want to move the original pointer pointing to this. So as in, if I try to print s pointer bar, that will not happen. So let's try do that. Sorry for some errors and okay, it's not actually uh, throwing it, but anyway, the idea is that bar, the object is not is not with yeah, sorry for that. Yeah. So basically the idea is that now I can call q pointer with this f function because q pointer now owns that object, right? So it will print this f bracket construct something that gets printed here. Okay. Now this goes out of scope, right? So hence the destroying qptr is gets called. I mean, it will get out of scope, but I printed this to actually to point out that because this is going out of scope, Q pointer gets out of scope, so it will get destroyed. And the good thing is, because it's a standard unique pointer, it will automatically take care of that. Okay. Next, I can call the same as pointer with as pointer bar again. Okay. Because I call bar, it prints foo bar, right? And finally, because this unique function make unique was called with the constructor of foo, right? So there's an object to it. Its destructor will get called because S pointer goes out of scope. Okay, for this class. So this part, which is the tilde foo, that gets called. Okay, I really encourage you guys to actually maybe comment each of the portion and see which portion is printing what, which I just explained. Okay, so that you understand yourself what just what this whole piece of code actually does. But essentially, the idea is that unique pointers are used to have a unique instance of a pointer. And there are two main things that you need to understand. When the constructor gets called, resource acquisition happens. So we'll initialize the pointer to store the raw pointer. Okay, so we'll wrap that raw pointer, in this case, the underscore PTR or whatever we're passing after the new. Okay, so we wrap that new wrap that raw pointer to a object of a class, right? So that we can use the properties of the class now. Like the constructor gets called, the constructor then initializes the object. Okay, so that's the RII. And when the destructor gets called, which happens when your object will go out of scope, that it will just delete that raw pointer. Okay. So because this happens automatically, you don't have to worry about managing memory. Okay. Right. So this is essentially how smart pointers work. Okay. And yeah, so this was unique pointer, as in the idea is that a given object can be pointed to by only one pointer, a one smart pointer. Okay, so that's the unique pointer. Now, any questions so far? Okay. But what if I want to, what if I want to work with many pointers pointing to the same object? Okay, so that's something we saw here, right? So maybe B and A were many pointers pointing to the same object, right? And here it's the example of unique pointer. So unique pointer will save us in this case, where my class would have returned a pointer, and when I set it to null or something, right, it um, doesn't really care if your raw pointer will probably be set on something, but because it's an object, right, it's a private member, you cannot change it anyway. Remember here, smart pointers and that pointer which internally it stores, right? Because it's a private member, anyway, it's not accessible and you cannot change it outside the class. So with something like that in back of our mind, making mistakes like this is harder in smart pointers. Okay. And essentially the idea here is also same. I want only one object pointer to point to my new object. Okay. And when this object goes out of scope, that resource will get deallocated. So that was with unique pointer. To deal with something like this, where two pointers are pointing to the same object, and I do not want to double delete, right? After the ownership has already been removed, I can use something called shared pointers. So let's look at that. I'll have a string. So the include memory is needed for all these smart pointers. Okay. So all the smart pointers that like unique pointer, make unique and all that, along with what I'll show for shared pointers, that's under this header file memory. Okay. So I'll declare something called shared pointer. Okay. This time to take integers and the object will be P. So standard make shared, sorry, with integer and using the function. Okay. So this will make a shared pointer of integer. Okay. And I'm saying I will store 3 inside P. I'll dereference P and store the number 3 inside it. There is an interesting member variable function, you can say either way, which keeps track of what or how many objects pointers are pointing to the same object. And that's exactly what is used to keep track of uh, if the resource has been reallocated or not. Okay. So let's take the example. So one, that P is equal to pointer P and standard end line, standard layout. First is something called a reference count. Okay, so first with P's reference count. That's what we'll print now. Is p dot. So you can use dereference operator, not an issue. To get the reference count, you use count. Okay, and then end the length. Okay, so this function called use count keeps track of how many pointers are pointing to that object. Okay. Now, what I can do is I can make standard shared pointer, basically this one. Okay. If template as integer, basically same data type, but this time I'll make q and pass p to it. Okay. So the default behavior of such kind of syntax is that it will create another integer pointer, okay, pointing to the same object as p. As in, it will also store the same address of p. Okay. So this is the first line. This is the second one. Okay. Now, instead of p, it will be q. And I'll reference q. I'll dereference or just maybe just call it p. In fact, I can call it, you can use the same function for q also, but then it won't tell if p changed or q changed, whatever. I mean, it'll be the same, but anyway. I try to print p, fourth example. So p will print 3 because that's what we set. That's what we want here. Initially, the count will be 1. Okay, so the RC is basically the reference count. Basically, the reference count is how many uh, things are pointing to something. Okay, so here in this case, how many pointers are pointing to the same object is the reference count. And we use the use count function to keep track of it. Okay, all right. Q, if I dereference, also point to 3 because it's pointing to the same object. So dereferencing Q will give me the value 3. Now the reference count is 2 because Q is also pointing to the same object. P is also pointing to the same object. Okay. Here I should say P. Here I should put Q. Yeah. But yeah. So both of them have 2. Reason being, both of them are pointing to the same object. So the reference count for P, okay, is also 2. For Q is also 2. Okay. Now let's say I use the reset function. So the reset function, what it actually does is, we just look at that. So yeah, standard cout. Okay. It's 3 for the variable p. Now we can just see the reference count. Okay. So it actually, I think you can guess what it actually does. P dot is count. Standard and 9. Okay. Let's see what happens after the reset. So that is the reset to 0. Okay. Meaning that actually makes sure that your reference count goes to 0. Okay. As in, if you had a Q pointing to that same object, right? And P was initially holding that data. So making a reset essentially frees up whatever P was holding. In a way, you can also think whatever Q was holding. Actually, print that and see. Oh no, actually, I think Q will still hold it. Yeah, because we reset it from P, not for Q. So let's do that. Yeah, correct. So what happened? What actually happened is in this portion 3. So if you see 3 part, right? So with the reset, P no longer points to that object, right? Which had 3. We did not do that for Q. So the reference count was set to 0 for P, but if I try to find the reference count for Q, it still shows 1 because to that object now Q only points to it, no longer P points to it, right? Okay, I hope this example is clear, right? I can do another thing. So I can do P dot with reset. So because reset, if you don't pass anything, it's an empty pointer essentially. But what I can then do is pass a new pointer to it. Okay, so I'll call it int 11. That's it, right? So don't get confused here. Essentially, I'm passing a pointer. So this new keyword will return a new pointer of integer data type where the pointer has 11 as the value. Okay, so integer with bracket 11 is another way of telling I'm declaring a certain object of integer data type containing 11 and pointer of that I'm passing it to P. Okay, so this reset will change the ownership now. Earlier, P was pointing to something called something which contained 3. Now it will point to something containing 11. That's it. Okay. Um, let's do that. So this time I'll have it as 4 PRC. Okay. And I'll also try to print the value of P because why not? So this will have P count and here I'll just dereference P. That's it. Here I'm not touched. So that should still pointing to 3 and its reference count should be 1. Okay. Right. So if you see the fourth one, so reference count is 1 expected because now I've set it to some new pointer. It's now low note. It is no longer 0. Okay. Previously it was in this example, right? Because we just reset it to nothing. So whatever it was pointing to before, it's no longer points. Okay. It actually has no address. But now in this example, we reset it and now it's pointing to a new object. So hence the reference count is 1. And the value of that is 11. So that's what we see. Okay. Another thing one can do is have, let's say, a point to null pointer, right? And then I can try to print the reference count, right? The other thing is this one, but I cannot try to dereference and print because then that is not valid. It actually does not like point to anything. So dereferencing and printing is no, right? So printing this, so the reference count is 0. Okay, because it's actually not pointing to anything. The null pointer is essentially that. Okay, you try to dereference a null pointer, that's actually undefined behavior. You should not be doing that. Okay, maybe this will throw an error, but if it doesn't, in any case, yeah, this is a segmentation fault that happened. Good thing it actually threw an error. You should not dereference a null pointer because it actually is not pointing to anything. Okay. So yeah, I think that's about it. So yeah, so this is smart pointer with unique pointers, shared pointer, the shared pointer with its reference counts, and the main two concepts of in C++ with with the idea of scope, where you have RRID that you destroy when the destructor gets called. Okay, when anything goes out of scope of an object, the destructor will get called, and with it, we can release the resource. Okay. The other concept, RAI, where when the constructor gets called, as in when we are initializing something, an object of it, right? Then the constructor will get called. Then it will set or initialize the internal member variable containing or wrapping around the raw pointer. Okay. So these are the two main ideas which we use to define all kinds of smart pointers. And then we saw the two smart pointers. One is the unique pointer with, yeah, here if you try to get a reference count or anything, it will just always be one because it's a unique pointer. Okay. With shared pointers, you'll have multiple reference counts. And having zero means it's currently not pointing to anything, or it could be reset to point to something else. Okay. Or it could be just reset to point to nothing. You can have multiple objects created from the same smart pointer, shared pointer. Okay. So yeah, then the reference count will keep increasing as we saw in this examples. With this, these sessions for the course programming modern C++ for this cycle ends. Thank you for joining today's extra class. And what I would definitely encourage is go through all the topics that we covered all these weeks, practice them. They're available in the link that's shared with you guys. And the more you actually go into the code, make changes, run it, um, comment, uncomment stuff, the more you learn. And that's something I would encourage. And yeah, with that, I'll end. And if you have any questions, I'll be here. So feel free to ask. Yeah, with that, happy coding.